Okay, in this section we're going to talk about electrolysis and stoichiometry. The idea here is that the amount of substance that you reduce or oxidize in an electrolysis cell is directly proportional to the number of electrons passed through the electrolytic cell. And if you have counting things like number of electrons and so on, that means that you can do stoichiometry, just like we learned in Chemistry 107. Here's an important unit here. 1 amp, or ampere, is 1 coulomb per second. Ampere is a measure of current, and if you have a 1 amp current going through a particular place in the circuit, you transferred through that place in the circuit 1 coulomb of charge. And then recall that the Faraday, that's the proportionality constant between charge and mole of electrons, 96,485. So if we can determine the amount of current measured in amp for a particular time, we can determine the number of coulombs and divide that by coulomb per mole. We get the number of moles of electrons. And if we have the balanced oxidation reduction equation, we can figure out how much oxidized and how much reduced. Just to illustrate that point again, here's an electrolytic cell. And here we'll put something to be oxidized and reduced, not necessary to specify that. And here's a battery. This is our electrolysis cell. Make this a negative and make this a positive. And electrons, we said, go down the negative branch here, even though if you look at conventional current diagrams, you have something that goes like that. All right, so now we have electrons going down here. This is the cathode. And just for example, let's take something over here. This will be the anode. And for the cathode, let's put some, say, silver ions here. At the cathode, that's the silver ions, Ag+, will take up 1 electron to be reduced to silver, metallic silver. If we just pass through here 1 electron, then we will make 1 silver atom. If we pass through a mole of electrons going through here by passing a current over a particular time, a mole of electrons, then we will make 1 mole of silver ions. So you consider these electrons just as a reagent like we did in Chemistry 107. And the number of electrons transferred can be determined by the current times time divided by the Faraday. All right, so stoichiometry. So let's do some stoichiometry. A metal rod is made the cathode in an electrolytic cell containing nickel 2+. How many grams of nickel are plated on the metal rod if a current of 2.43 amp is passed through the cell for 10 minutes? All right, so 2.43 amp, that means we're putting through the cell a certain charge, coulomb per second. We multiply the time that current went through the cell. That will give us the total charge that went through the cell. We divide by the Faraday, and that will give the number of moles of electrons. And then we do the stoichiometry based on the balanced redox equation. Actually, here we only have to do a half reaction. Okay, so let's draw that cell here. Here we have nickel, and that's going to be reduced at the cathode. Here's our electrolytic cell. Here's our battery. Don't really care what's happening over here. This is a negative terminal. Electrons come down here, and they're going to go on to the nickel. Nickel 2+ is going to be reduced. We have to balance this half reaction. There are 2 electrons that we're going to stick on the nickel in order to form metallic nickel. All right, so let's do the calculation. 2.43 amp, that's 2.43 coulomb per second. We put that through 10 minutes. We want the total charge we put on there, so 2.43 coulomb per second. And there are 60 seconds per minute, and that was 10 minutes. So the total charge that went through the cell was 1.46 times 10 to the third coulomb. Well, how many moles of electrons went through the cell when we put 2.3 amps for 10 minutes? Well, that's where we use the Faraday. 1.46 times 10 to the third coulomb. The Faraday, 96,485 coulomb per mole of electron. So the number of moles of electrons that went through that cell was 1.51 times 10 to the minus 2 mole of electron. Now that's not how much nickel we produce, because for each mole of nickel we need to use up 2 mole of electron. So let's do that conversion. 1.51 times 10 to the minus 2 mole of electron. And then we said there are 2 mole, for 1 mole of nickel, we need 2 mole of electron. So the mole of nickel is, we do this, just divide this number by 2, it's 7.56 times 10 to the minus 3 mole of nickel 2 plus that we're going to reduce. And then to figure out how many grams, just multiply the mole of nickel by the molar mass of nickel. We look that up. That is 58.69 gram per mole of nickel. So the total amount of nickel that we played out on that electrode by passing a current of 2.3 amp for 10 minutes is 0.443 gram nickel. There we go. That's how you do stoichiometry and electrolysis. Here's a clicker question we didn't get to in class, but let's look at this anyway. Which one of the following is true for an electrolytic cell before any current has passed through the cell? So remember, for an electrolytic cell, you set it up and you don't turn on the battery yet. The reaction will not go as written. The reason that you have the battery in the circuit is to drive the reaction in a way that it wasn't normally going. So in fact, it's a non-spontaneous reaction. The electrolytic cell is non-spontaneous, and we make it spontaneous by putting the battery in the circuit. So non-spontaneous, delta G equals 0, that's not spontaneous. E cell greater than 0, if it's greater than 0, that's not spontaneous. In fact, that's spontaneous. So K is less than 1. Actually, that should be, well, K less than 1. Okay, let's go on to another example. Here are 2 examples on this slide. Given that the cell EMF for this particular reaction, or this particular cell, given in this standard cell notation, where X here, we don't know what X is, given that the cell EMF for this is 1.10 volts, what is the identity of X? And we're given the standard reduction potential of zinc, 0.76. Okay, well, let's take a look at this. This is 1 molar, and the concentration of this unknown is 1 molar. So that means what we have are standard cell potentials. So in fact, this E0 here is a standard cell, or this voltage here is E0, the standard cell potential of this, because all the concentrations are 1 molar. Remember, let's go to the next slide here, that E0 is E0 of the cathode minus E0 of the anode. Okay, so if we go back here, oh look, we know what the anode is. It's zinc being oxidized. We don't know what the reduction is here. And we given this. So it looks like, but we know what cell voltage is. So it looks like we have two of these three quantities. So here we have zinc being oxidized to zinc 2 plus 2 electrons. And then this says that's what's being reduced. We don't know what that is. X2 plus going to X. So we'll put 2 electrons on X2 plus, and that will give us X. All right, this looks like the anode. This is a cathode. So look at the E0. E0, standard cell voltage for zinc, was given in the problem. It's minus 0.76. I think that was a minus sign there. Yeah, there it was, minus sign. The cathode, we don't know what that is. Let's give it the symbol X. But we know what E0 is from the problem. That was 1.10 volts. So just let's put that down here, 1.10 volts. E cathode, we don't know what that is, minus E anode, minus 0.76. So we find out X, that's the standard cell voltage for our unknown reaction here. X is equal to, let's just see, I did that calculation here, 0.337 volts. I think that's a positive, yes, positive number. So this is E0 for our unknown X. Well, what we do is just look up in a table of standard reduction potentials, figure out what X corresponds to 0.337. All right, here we have 0.337. 0.337. Well, let's see. Well, 337 is close to 34, so there's a standard plus 34 is copper. Copper has that standard reduction potential, as does vanadium 2 plus, and maybe you might say this, but let's take it copper. We actually have two choices here. We might as well take copper because we don't know what vanadium oxide 2 plus really is. So, well, I suppose we should put them down both. So X could be copper 2 plus, or that vanadium oxide 2 plus, because both of those have a standard cell voltage of 0.34. 0.34, 0.34. Could be one of these two things here. All right. Now, let's do this second example in this slide. Let's see if this following reaction is spontaneous at 25 degrees. Now, in contrast to this example where you have 1 molar, so you just have to figure out what standard cell voltages are. For this case, you have non-standard state conditions, so we're going to have to use the Nernst equation. Okay, so let's do that. Well, first of all, let's write down what the two reactions are. Zinc going to zinc 2 plus, and silver plus going to silver. Okay. So zinc is being oxidized to zinc 2 plus 2 electrons, and silver plus 1 is being reduced by adding 1 electron to metallic silver Ag. Since we're going to have to use a Nernst equation, we're going to have to calculate a reaction quotient. And so we have to have a balanced chemical equation. So we have to multiply this by 2. So we have 2 electrons on this side, 2 electrons on that side. So our balanced chemical reaction is zinc plus 2 silver ion goes to zinc 2 plus 2 silver ions. This is metallic silver. And let's see, 2 plus, that's balanced, 2 zinc, or 2 silver, 1 zinc, that's balanced. So there's the balanced chemical reaction. Now the Nernst equation, E is equal to E0 minus, that's why I always get confused, I always use put plus there, RT over NF times the natural log of the reaction quotient. All right, let's calculate some of these. E0 is E0 for the cathode minus E0 for the anode. E0 for the cathode. Given in the problem, the cathode is where the reduction occurs. That's silver, 0.7996. Ooh, lots of significant figures. Minus E anode. E anode, given in the problem, was, and I have to go look at it again. E0, let's see, anode, that's where it's being oxidized, zinc, 0.7 minus, don't forget the minus sign, 0.7628. So E for the cell comes out to be 1.5624 volts. RT over F, remember that was 0.02569. N for this equation, we have 2 electrons, so N is equal to 2. And finally, Q for this is equal to the reactance, which is zinc 2 plus, concentration of that. Silver is a solid, does not appear in the equilibrium expression. Reactance, silver plus raised to the second power. So there's the reaction quotient squared. All right, and given in the problem, the zinc concentration was 0.012 molar, and the silver concentration was 0.2 molar. So this is 0.012 down here, 0.2 molar, and we square that. So now we have everything in here to calculate the cell voltage. Why are we calculating the cell voltage? Well, the question asked, is the following reaction spontaneous? So if we calculate the cell voltage and find that it's greater than 0, the reaction will be spontaneous. And if it's less than 0, the reaction will not be spontaneous. So let's go ahead and calculate, ignore that for a minute. E will be E0, which we said was 1.5624 volts, minus RT over F, which was 0.02569, divided by N, which was 2, times the natural log of the zinc concentration, 0.012, divided by the concentration of silver, which was 0.200 squared. And you calculate this, it comes out to be 1.5. This is a negative number, which means that this will be a positive, so you're adding on to this, 1.5779 volts. So this implies that reaction is spontaneous, or in other words, E for the cell is greater than 0, and that also implies that delta G for that reaction as written with those concentrations, delta G is less than 0. Because remember, which I always forget, delta G is minus, oh, that's a minus sign, minus NFE. All right, so we've done that problem. Those two problems, the reaction is spontaneous. Let's do another example. How many grams of chlorine gas are produced by passing 1,000 amps, a kiloamp of current for 1 minute through an aqueous solution of sodium chloride? This looks like a straightforward stoichiometry problem. We have a certain amount of charge per second being passed through the cell. For 1 minute, we multiply the number of seconds times that. That'll give us the amount of charge. We use the Faraday to convert the charge to mole of electron, and we use a balanced chemical equation. to convert the mole of electron to grams of chlorine gas. Okay, well, let's go ahead and do that. Let's see, it's around here somewhere. I have my notes spread out here. Chlorine gas, here we go. All right, so 1,000 amps, 1,000 amp. That implies we have 1,000 coulomb of charge per second passing through the cell. Well, let's see. 1,000 coulomb per second. And we pass that through 1 minute. And I vaguely recall that there are 60 seconds per minute. So that comes out to be 6 times 10 to the 4th coulomb. That's how much charge we pass through there. How many electrons does that correspond to? Well, 6 times 10 to the 4th coulomb, ignoring significant figures here, divided by 96,485 coulomb per mole of electron. So this comes out to be 0.622 mole of electron. So is that equal to the mole of chlorine gas? Well, we don't know yet. Let's actually write down that half reaction. It's a sodium chloride solution. So chloride, looks like we're going to have to put a 2 there to get chlorine Cl2 gas. And how many electrons are going to be taken off? Looks like we have 2 electrons. So for each, we need 2 mole of electron to produce 1 mole of Cl2. So it's just like Chem 107. You have to convert in stoichiometry, stoichiometric coefficients and so on. So mole of electron. And for 2 mole of electron, well, I guess I've done this backwards here. So let's do it this way. For 1 mole of Cl2 gas, we need 2 mole of electron. So the number of moles of chlorine that we produce by passing 1,000 amps for 1 minute through the solution is 0.311 mole of Cl2. And then how many grams? Well, 0.311 mole Cl2 multiplied by the molar mass, which is 70.9 gram per mole. And that comes out to be 22 grams of Cl2. So that's how much chlorine we can produce with that cell system. All right, 1 more, or maybe 2 more. This might be the last one here. Yeah, probably. All right, so let's do copper sulfate. This is placed in an electrolysis cell to plate out copper. Copper is reduced and H2O is oxidized at the anode. Well, that's nice. Tell us what to do. We don't have to write down the half reactions or figure out what they are. We pass current through the cell until 5 liters of O2 is produced at 1 atmosphere and 0 Celsius. That's how you measure the volume of O2. If the volume of the solution is 750 milliliters, what's the pH after electrolysis? Well, you maybe want to pause this recording and think about it for a while. Looks like it's going to be an electrochemistry problem because you're doing electrolysis, but if you think about it, maybe not. So let's actually explore this. Let's write down some half reactions. So copper, it said copper is going to be plated out, so we're going to have 2 electrons there. This occurs at the cathode. The cathode. And then at the anode, we said that we're going to oxidize water. What's going to be oxidized in water is the oxygen going from -2 oxidation state to 0. We just make O2 gas, so 2H2O. That we reduce to O2 plus 4H plus and plus 4 electrons. And that happens at the anode. Water is oxidized to produce O2 gas. All right, so we've written down a couple reactions. What's given here is how much oxygen is produced. So what you're given is the amount of oxygen produced. Oh, look. If you produce 1 mole of oxygen, you produce 4 moles of H+. How many moles of oxygen did you produce? Well, you can convert the volume of oxygen at atmosphere at the pressure and temperature, PV equals nRT. So we can figure out how many moles of O2 you produced. How many moles of O2 you produced? Well, and multiply that by 4. That's the number of moles of H+ you produced. And, okay, moles of H2 divided by volume will give you the molarity. And the molarity then will give you, if you take minus log of it, give you the pH. So it looks like we don't have to do any electrochemistry here, any stoichiometry, use the Faraday or amps or anything. All we got to do is to figure out how much O2 we made. That'll give you how much H+ you made, and that will give you the pH. So let's do that. We made 5 liters of oxygen, and maybe you remember this trick at 1 atmosphere and 0. That's standard temperature and pressure for gases. At STP, there are 22.4 liter per mole. Handy shortcut. Or if you want, you can use PV equals nRT. So this means that we've made 0.223 mole of O2. 0.223 mole of O2, and we have 4 mole of H+ per mole of O2 from this balanced half reaction. We didn't really need to even use this reduction. We just need the half reaction, the relationship between O2 produced and H+ produced. This doesn't produce any H+ or OH-. So that comes out to be 0.893 mole of H+. And we know that mole of H+ is in 750 milliliters, or 0.75 liter. So we can figure out what the concentration is of H+. 0.893 mole of H+. We have that in 0.75 liter. So the concentration is 1.19 molar H+. And the pH, remember, is minus log of the hydrogen ion concentration in molar. So this would be minus log of 1.19. So the pH comes out to be 7.57 times 10 to the minus 2. So there we go. It's electrolysis looking problem, but in fact it was just a Chem 107 stoichiometry problem looking at ratios of stoichiometric coefficients. So I think that's about it. Yeah, these are examples of voltaic cells. Maybe I'll cover that in a different YouTube lecture. So thanks for listening.